Hello students, welcome to the second part of the gear trains. In this presentation, we will look at the remaining two types of gear trains, that is reverted gear train and the epicyclic gear train, and how the velocity ratio or speed ratio in each of the gear train is determined. The reverted gear train. When the axis of the first gear, that is first driver, and the last gear, that is the last driven or the follower, are coaxial, then the gear train is known as reverted gear train, and as shown in figure here. Now, when the axis of the first gear, that is gear 1, which is driver, and the last gear, that is driven, so gear number 4 here, this is the driven gear or the follower gear. So the driver, first gear, and the last gear, driven gear, their shaft axes are coaxial, they are in the same line. If this is the case, then the gear train is known as reverted gear train. And here it should be noted that gear 2 and 3, they are mounted on the same shaft, hence 2 and 3 form the compound gear. So reverted gear train may contain compound gear also. In this figure, we see that gear 1, that is this one, is the first driver, drives gear 2, this one, that is first driven or the follower, in the opposite direction. Right? So this rotates in the clockwise and gear 2 rotates in the counterclockwise. Since gears 2 and 3 are mounted on the same shaft, therefore they form a compound gear, and the gear 3 will rotate in the same direction as that of the gear 2. Gear 3 also rotates in the counterclockwise direction as that of 2. Now, the gear 3, which is now the second driver, this one is the second driver for the gear 4, means gear 3 will drive the gear 4. So this is the last driven of the follower, and the sense of rotation of gear number 4 is in the same direction as that of the gear 1, means gear 1 and gear 4, they rotate in the same direction. Now thus we see that in a reverted gear train, the motion of the first gear and the last gear is same. So when you want such a kind of motion, then also you can go for reverted gear train. Now let T1 be the number of teeth on gear 1 here, and R1 be the pitch circle radius of gear 1, and N1 be the speed of gear 1 in RPM. Similarly, T2, T3, T4 be the number of teeth on the gear 2, gear 3 and gear 4, and R2, R3, R4 be the pitch circle radii of gear 2, gear 3, gear 4, and finally N2, N3, N4 be the speeds of gear 2, gear 3 and gear 4 in RPM. Now, since the distance between the centers of the shafts of gears 1 and gear 2 as well as gear 3 and gear 4 is same, we can write R1 plus R2 equal to R3 plus R4. So, the radius of gear 1, radius of gear 1 plus radius of gear 2 equal to radius of gear 4 plus radius of gear 3. Right? So, from the figure itself, it is very clear that radius of gear 1 plus radius of gear 2 will be equal to radius of gear 3 plus radius of gear 4, because this distance between these two centers is same. So hence the radii of 1 and 2 must be equal to radii of 3 and 4. Let that be question number 1. Now also the circular pitch or module of all the gears is assumed to be same. Therefore the number of teeth on each gear is directly proportional to its circumference or radius. So this can be written proportionally as T1 plus T2 equal to T3 plus T4. And now speed ratio for this reverted gear train can be written as product of number of teeth on the drivens divided by product of number of teeth on the drivers. So N1 by N4 the speed ratio between N1 and N4 equal to T2 T4 number of teeth on gear 2 multiplied by number of teeth on gear 4 divided by number of teeth on gear 1 multiplied by number of teeth on gear 3. Right? So this is the explanation for this. So the speed ratio between gear 1 and 2 is N1 by N2. Similarly, the speed ratio between gear 3 and 4 is N3 by N4, which is equal to T2 by T1 into T4 by T3. As N2 and N3 are mounted on the same shaft, their speed will be equal. Hence, N1 by N4 equal to T2 by T1 into T4 by T3. So from equations 1, 2 and 3 you can determine the number of teeth on each gear for the given center distance, speed ratio and module only when the number of teeth on one gear is chosen arbitrarily. If the number of teeth on any one of the gear is chosen arbitrarily, then other things can be determined very easily. Means the speed of the remaining gears. So the reverted gear trains are used in automotive transmissions, lathe back gears, industrial speed reducers, and in flops where the minute and the hour hand shafts are coaxial. Then the last type of gear train is the epicyclic gear train, also called as planetary gear train, because this gear B rotates around this axis O1 in a similar manner to a planet rotating about some center point. The epicyclic gear trains are useful for transmitting very high velocity ratios with gears of moderate size in a comparatively lesser space. When the space is available is less, and when you require very high velocity ratios, and when the size of the gear train is moderate, then we prefer the planetary gear train or the epicyclic gear train. The epicyclic gear trains are used in the back gear of lathe, differential gears of automobiles, hoists, pulley blocks and wristwatches. So this is sample figure of the epicyclic gear train. Now in this figure, gear A and RC, this is RC, have a common axis at O1. Gear A and this RC, they have the common axis of rotation and the center is O1. The gear B, this one, meshes with gear A, this gear, and has its axis on the arm at O2. So this gear, that is B, will rotate about the point O2, which is on this arm. Now in case if the arm is fixed, let us assume the arm is fixed, then the gear train is simple. When this is fixed, the A and B constitute a simple gear train, and gear A can drive gear B or vice versa. If gear A is fixed, if this is fixed, then what will happen? And the arm is rotated about the axis of the gear A, that is about O1, then the gear B is forced to rotate upon and around gear A. That is very important, and that gives the meaning of epicyclic gear train. Around gear A, such a motion is called as epicyclic. Epicyclic means upon and around a gear, means B rotates upon A and also around A about the center. Hence this arrangement is called as epicyclic gear trains. And the gear trains arranged in such a manner that one or more of their members move upon and around another member are known as the epicyclic gear trains. So epi means upon and cyclic means around, hence the epicyclic gear train. So B will move upon gear A and also around the gear A, hence this entire thing constitutes epicyclic gear train. Now how the velocity ratio in case of epicyclic gear train is calculated? There are two methods. One is the tabular method and second is algebraic method. Let us have a look at each of these. First one, we will see how the tabular method is used to determine the velocity ratio in epicyclic gear train. Now, for this, you should keep in your mind the convention used for the sign of rotation of the gears. Here, we are assuming that the anti-clockwise rotation of gear as positive, anti-clockwise as positive, and clockwise rotation as negative. Students, you can also assume other way also, means clockwise as positive and anti-clockwise as negative, but throughout the solution you have to follow the same convention. That is very important. Now, let TA be the number of teeth on gear A and TB be the number of teeth on gear B. Then, as the name says, tabular method, you have to prepare a table. So the first column is step number. So in step number, what we do? We fix the arm C, we are fixing. In most of the problem, this is the first step. In epicyclic gear trains, the arm is fixed. And the gear which is mounted on the same axis is given +1. +1 means in the anti-clockwise direction. Means arm is fixed and then gear A is given only one revolution in the anti-clockwise direction. So in that case, what will be the revolutions of the elements of this gear train? So there is arm C, there is gear A and gear B. Under these, the revolutions are listed. And this first row is very important. Once this row is written correctly, then remaining 3 rows you can easily write. So revolution of arm C is 0 because it is fixed. Arm fixed, hence its revolution is 0. And what are the revolutions of gear A? We have, as it is stated here, we are giving only one revolution to gear A. So hence +1. Plus means in the anti-clockwise direction. Then what is the speed of gear B? So it is nothing but minus TA by TB. TA by TB. Because just you take the ratio of the speed of gear A and gear B. It is NA by NB. Speed ratio is NA by NB. Now NA by NB equal to TB by TA. Following, NA by NB equal to TB by TA. So as NA equal to 1, right? NA equal to 1. And from this ratio, if you substitute NA equal to 1, you will get the speed of NB equal to TA by TB. It is minus because it is rotating in the clockwise direction. Follow? Just write down the equation NA by NB equal to TB by TA. Substitute in that equation NA equal to 1 and rearrange the terms. You get NB equal to TA by TB minus because this is rotating in the clockwise direction. This step is very important. Then in the second step, what you do? Again, the arm is fixed and instead of one revolution, the gear A is given X number of revolutions in the anti-clockwise directions. Again, arm C is fixed, hence its revolutions are 0, but gear A is given plus X revolutions in the anti-clockwise direction instead of 1. So hence the speed of gear B becomes X times this, minus X into TA by TB. Then in the third step, what will do? Add plus Y revolutions to all elements. To all these we add Y revolutions. As a result, total motion of each of the element becomes, this is for arm C it is plus Y, for gear A it is X plus Y, and for gear B it is Y minus X into TA by TB. So once this is completed, that means this table is completed, then based on the given initial conditions, using these equations or any of these, the speed of these members can be easily determined. Now let us go to the second method, that is algebraic method, by using which the velocity ratio, speed ratio of a epicyclic gear train can be determined. In this method, the motion of each element of the epicyclic gear train relative to the arm is set down in the form of equations, algebraic equations you have to write. The number of equations depends upon the number of elements in the gear train, but the two conditions are usually supplied in any epicyclic gear train, namely, first one, some element is to be fixed. In the epicyclic gear train, some element has to be fixed, mostly it is the arm. And second condition is the other element has specified motion, means some other gear will have some motion, known motion. If these two conditions are given, then the algebraic equations can be easily solved. So these two conditions are sufficient to solve all the equations and hence to determine the motion of any element in the epicyclic gear train. This is the algebraic method explained. For the same gear train, let the arm C be fixed, this be fixed in an epicyclic gear train, and therefore the speed of the gear A relative to arm C can be written as Na minus Nc. Speed of gear A relative to arm C. Similarly, the speed of the gear B relative to arm C can be written as Nb minus Nc. Now, since the gears A and B are meshing directly, therefore they revolve in opposite directions. Then its speed ratio can be written as Nb minus Nc. Nb minus Nc means the speed of gear B relative to arm, and this is the speed of gear A relative to arm, which is equal to Ta by Tb. Okay. Since the arm C is fixed, hence Nc will be equal to 0. If you substitute Nc equal to 0 here, the ratio becomes Nb by Na equal to minus Ta by Tb. And in case if gear A is fixed, then Na equal to 0. If you substitute Na equal to 0 here, you will get Nb divided by Nc equal to 1 plus Ta by Tb. So these are the two conditions. One of the element has to be fixed, either this or this. And if out of these any one speed is known, these two equations, set of equations, can be solved for the unknown. Now note here, the tabular method is easier and hence mostly used in solving the problems on epicyclic gear train. So tabular method is easier, hence it is preferred. Let us consider an example. This is the epicyclic gear train. An arm carries two gears A and B having 36 and 45 teeth respectively. If the arm rotates at 150 rpm in the anti-clockwise direction about the center of gear A, which is fixed, determine the speed of gear B. If the gear A, instead of being fixed, makes 300 rpm in the clockwise direction, what will be the speed of gear B? So let us solve this problem by tabular method. So here, what are the given things? Number of teeth on gear A 36, number of teeth on gear B 45, and the speed of the arm, the C 150 rpm in the anti-clockwise. Okay, so now by using this tabular method, prepare table like this. Column 1 is the step number, conditions of motion, and revolutions of each of the elements. There are three elements here: arm, gear A, gear B, arm C, gear A, and gear B. Now, as usual, what we will do, we will fix the arm and give one rotation to gear A in the anti-clockwise direction. As a result, what will happen here? The speed of the arm will become 0 because it is fixed, and the speed of the gear A is +1, and the speed of gear B is minus TA by TB. So here it is how we get NB equal to T by TB. So NA by NB equal to TB by TA, but NA equal to +1. So hence if you substitute NA equal to +1, you get NB equal to TA by TB. So minus because it rotates in the opposite direction to that of A. Now second step, arm fixed. Again keeping the arm fixed, instead of +1 we give +x revolutions to this gear A. So gear A will now have +x revolutions. As a result, the gear B will have -x into TA by TB revolutions. Add +y revolutions to all the elements. As a result, the total motion of each of the element becomes arm C plus y, gear A x plus y, and gear B y minus x into TA by TB. Now, speed of gear B when gear A is fixed, the first part of the problem. Since the speed of the arm is 150 rpm in the anti-clockwise direction, therefore from the fourth row of the table we get y equal to 150 rpm. So here also the gear A is fixed, therefore x plus y equal to 0. Gear A is fixed, x plus y equal to 0. That means gear A is fixed, hence the total motion of the gear A is x plus y. As it is fixed, will be equal to 0. X plus y equal to NA. As A is fixed, NA will be equal to 0. Hence the equation is total motion of gear A is x plus y equal to 0, or x equal to minus y, means x equal to minus 150 rpm. Now the speed of gear B is given by using this relation, NB equal to y minus x into TA by TB. X we know, TA we know, TB we know. Hence we get speed of gear B as plus 270 rpm. Plus means in the anti-clockwise direction. Now second part of the problem. To determine the speed of the gear B when gear A makes 300 rpm in the clockwise direction. So here it was fixed, but now here it is rotating at 300 rpm in the clockwise direction. Since the gear A makes 300 rpm in the clockwise direction, therefore from the fourth row of the table x plus y is equal to minus 300 clockwise. So hence x equal to minus 450 rpm. Hence speed of the gear B will be equal to NB equal to minus y minus x into TA by TB. So substituting all the values, you get speed of the gear B as 510 rpm in the anti-clockwise direction. So simple method. Okay. By using the algebraic method, let us see how the same problem can be solved. NA is the speed of the gear A, NB is the speed of gear B, and NC is the speed of arm C. Assuming the arm C to be fixed, speed of gear A relative to arm C is NA minus NC, and similarly speed of gear B relative to arm C is NB minus NC. Since the gears A and B revolve in opposite directions, therefore NB minus NC divided by NA minus NC equal to minus TA by TB. Now first part of the problem, speed of gear B when the gear A is fixed. When gear A is fixed, the arm rotates at 150 rpm in the anti-clockwise direction. So hence using this information, what you get, NB equal to 270 rpm. Similarly, second part of the problem, speed of gear B when A makes 300 rpm in the clockwise direction. Since the gear A makes 300 rpm clockwise, therefore NA equal to minus 300 rpm. Again using this previous relation, substitute the known values and get the value of NB. So it is 510 rpm, which is equal to that of which is obtained in the tabular method. So that is the end of the part 2, students. In part 3 we will try to solve some more problems on epicyclic gear trains. Thank you so much.